The origin of life is a question that has haunted humanity for centuries. How did the first living organisms emerge in our vast, ancient universe? Was it a cosmic accident, a divine spark, or something science has yet to fully explain? We are about to explore 30 mind-bending theories that attempt to solve this fundamental mystery. You will discover ideas ranging from life arriving on comets to the possibility of its beginnings in the crushing depths of the ocean. We will investigate if the first genetic code was printed on clay and whether life's spark requires a specific cosmic setting. By the end, you will have a complete picture of the most compelling scientific narratives for how biology began. Did life start on our planet at all, or are we all descendants of interstellar travelers? What do you believe is the most plausible starting point for existence itself? Perhaps the seeds of life were not planted here at all. The first theory we explore is called Panspermia, a profound idea suggesting life arrived on Earth from the depths of space. Imagine microscopic organisms, the most basic building blocks of biology, journeying across the cosmos. They could have been passengers inside a comet, shielded within the icy heart of an asteroid, or even drifting on microscopic grains of interstellar dust. The vacuum of space is bitterly cold and flooded with radiation, conditions that seem utterly hostile to life. Yet we know that certain extremophile bacteria on Earth can enter a state of suspended animation, surviving for astonishingly long periods without water or air. If such resilient life can exist here, could similar microorganisms have endured an interstellar voyage protected within a rocky spaceship? The evidence for this is not merely speculative. Scientists have repeatedly found amino acids on certain types of meteorites. Amino acids are the fundamental organic compounds that link together to form proteins, the very machinery of life as we know it. Finding these complex molecules on rocks from space tells us that the universe is already busy with chemistry, manufacturing the ingredients for biology long before planets even form. This single idea has a staggering implication. If life did not begin on our world but was merely delivered here, then it is possible, even probable, that the same thing has happened on countless other worlds. The origin story of every living thing you see, including yourself, may not be confined to the early Earth. It might be written in the stars, a cosmic legacy shared across the galaxy. But what if the story of life is not about a journey from the stars, but a transformation from right here at home? This is the theory of abiogenesis, the idea that life emerged naturally from non-living matter on the young Earth. Picture our planet over 4 billion years ago, a vast and violent world. Its skies were thick with volcanic gases, laced with methane and ammonia, and its vast oceans were warm, rich with simple chemicals washed from the land. Scientists like Alexander Oparin and J.B.S. Haldane called this mixture the primordial soup, a potent broth where the first spark of life could have been kindled. The crucial question was whether this soup could cook up the building blocks of life all on its own. In the 1950s, two researchers, Stanley Miller and Harold Urey, put this idea to the test. They built a remarkable device, a closed loop of glass flasks and tubes meant to mimic the early Earth. One flask held water for the ocean, another was filled with gases for the atmosphere. Then they sent sparks of electricity through the gas, simulating the intense lightning storms that would have been common. The results were astonishing. After just 1 week, the water turned a murky red and brown. The simple chemical soup had transformed, now teeming with amino acids, the very same organic compounds that form the proteins essential for all living cells. This was a monumental discovery. It proved that the fundamental ingredients of life could arise from simple, non-living components with just a little energy input. The next steps in the story are even more profound. In that ancient ocean, with energy from lightning, volcanic heat, and the sun's ultraviolet light, these amino acids could have begun linking together. They might have formed tiny chains, then longer strands, eventually creating proteins and other complex molecules. Over millions of years, these molecules could have organized into structures that learned to copy themselves, perhaps using a primitive version of RNA, a close cousin to DNA. The path from chemistry to biology is the greatest puzzle of all. How did a collection of molecules cross the threshold and become something we would call alive? The primordial soup theory provides a compelling starting point, a recipe for how our planet could have become a cradle for life. But this still leaves a deeper mystery. How did these complex chemical pieces find each other in the vast, diluted ocean? Perhaps the answer is not in the open water, but in the most extreme and isolated places on Earth. The open ocean was a vast and diluted soup, but the deep sea held a very different kind of kitchen. Far from the sun's reach, at the crushing bottom of the ancient ocean, lie hydrothermal vents. These are colossal chimneys on the seafloor, constantly billowing out superheated, mineral-rich water from deep within the Earth itself. In this absolute darkness, under immense pressure, a remarkable chemistry unfolds. The water spewing from these vents is not just hot, it is packed with dissolved chemicals like hydrogen sulfide, which provides a potent source of energy. This is a world that runs not on sunlight but on geothermal power. The theory suggests that these vents were the perfect crucibles for life. Their rocky structures are not solid but filled with tiny pores and compartments, almost like a natural sponge. Imagine these microscopic chambers acting as the very first protective cells. Inside them, the rich chemical broth from the vent fluid would become concentrated. Organic molecules like amino acids formed elsewhere or right at the vent would be trapped together, bumping into each other far more often than they ever could in the open water. These porous walls offered shelter and a stage, a place where simple molecules could meet, link, and begin the long, intricate dance towards complexity. The energy to power these first reactions was not from a lightning strike in the sky, but from the constant, reliable heat and chemical gradients of the vent itself. How did a collection of molecules become a self-sustaining system? Perhaps it was within these rocky, protected chambers in the eternal night of the deep sea that the first living cell learned to harness the Earth's own inner fire. Yet the leap from chemistry to a living cell demands a molecule of astonishing capability. It would need to carry instructions, a blueprint for building more of itself, and it would also need the tools to do the building work. This brings us to a theory centered on a single, multifaceted molecule, RNA. The RNA world hypothesis proposes that before the sophisticated partnership of DNA and proteins ever existed, the earliest life forms were based entirely on RNA. RNA, or ribonucleic acid, is a close chemical cousin to DNA. Its genius lies in its dual nature. Like DNA, it can store genetic information in its sequence of building blocks, acting as a blueprint. But unlike DNA, certain types of RNA can also act as enzymes, speeding up specific chemical reactions. This means a single RNA molecule could theoretically be both the architect and the builder, the instruction manual and the factory machine. It could potentially copy itself or assemble other molecules necessary for life, all without any help. Imagine a world not of cells, but of these self-replicating RNA strands floating in the ancient seas or trapped within the pores of a hydrothermal vent. The most successful replicators would become more numerous, slowly evolving through random copying errors. Over vast stretches of time, this molecular competition could have given rise to increasingly complex systems. Yet this elegant idea faces a significant challenge. RNA is a relatively fragile molecule. In the harsh conditions of the early Earth, it might have broken down too quickly to establish a lasting foothold. Scientists are actively investigating how the first RNA molecules might have formed from simpler chemicals and how they could have been protected. The transition out of the RNA world is another great puzzle. The theory suggests that eventually a division of labor emerged. DNA, which is more stable and better for long-term information storage, took over the role of the blueprint. Proteins, which are far more versatile and efficient as workers, took over the catalytic jobs. RNA was left as the crucial messenger between the two. This progression from a one-molecule show to a specialized three-part system could have been the key step that allowed life to become more robust and complex. So the question remains, where did these first self-copying RNA molecules come from? Could their components have been forged in the depths of space itself? The delicate fragility of RNA presents a profound puzzle, but nature often provides a scaffold for complexity to arise. Another compelling theory suggests that life did not emerge in the open water or deep sea vents alone, but on solid ground within the mud and clay of the early Earth. This is the clay catalyst hypothesis. The idea is that the very first steps toward biology were guided not by a molecule, but by a mineral. Certain types of clay, like montmorillonite, have a very specific physical structure. Their surfaces are not smooth, instead, they are covered in a perfectly repeating crystalline pattern of positive and negative charges. Think of this surface as a template, a molecular mold. In the shallow pools and riverbeds of the primordial world, simple organic molecules like the building blocks of RNA would have been naturally attracted to these charged clay surfaces. They would stick to the clay, lining up in neat rows according to the pattern of the template. This organization is crucial. By holding the molecules in close proximity and in the right orientation, the clay dramatically increases the chance that they will link together, forming longer and more complex chains. It acts as a catalyst, a passive workbench that enables the construction of polymers without being consumed in the process. Laboratory experiments have powerfully demonstrated this effect. When scientists mix the basic components of RNA in a solution with clay minerals, they observe the rapid formation of RNA-like chains, sometimes dozens of units long. Without the clay, these same components might never connect or do so at an impossibly slow rate. This suggests that the inanimate mineral world played an active, guiding role in our origins. The first genetic material may not have had to form spontaneously in a chaotic soup. Instead, it could have been patiently printed line by line on a crystalline surface that predated life itself. The clay provided order, a fundamental principle that biology would later perfect. So, if minerals could organize molecules, what other environments held a similar creative power? Could the answer lie not on the surface of the Earth, but in the very sky above it? While clay provided a template on the surface, a far more energetic foundation was brewing in the deep. The iron-sulfur world theory shifts the stage from the sunlit shallows back to the volcanic fury of hydrothermal vents, but with a radical new protagonist. Proposed by the scientist Gunther Wechtershauser, this idea suggests life did not begin with a replicating molecule, but with a self-sustaining chemical reaction. It is a metabolism-first origin story. The central actors are minerals like pyrite, also known as fool's gold. These iron sulfide crystals form naturally at hydrothermal vents, and their surfaces possess a remarkable chemical power. Wechtershauser envisioned these shiny, metallic surfaces as the first metabolic platforms. In this scenario, the raw materials were the volcanic gases bubbling up from the Earth's mantle, like carbon dioxide and hydrogen sulfide. When these gases came into contact with the catalytic surface of the iron sulfide mineral, they could react, releasing energy and fixing carbon into more complex organic molecules. Think of the pyrite surface not as a passive workbench, but as a powered assembly line. It provided both a solid, structured foundation for molecules to gather and the very electrical and chemical energy needed to forge them into the building blocks of life. This would have created a primitive but self-perpetuating cycle. The energy released from one reaction would fuel the next, drawing in more raw materials and producing a growing diversity of organic compounds right there on the mineral surface. This cycle would be the precursor to metabolism, the foundational chemistry that all life uses to generate energy and grow. The great innovation here is that genetics came later. Before any molecule learned to copy itself, a sustainable, complex web of chemical reactions had to be established. This metabolic network could have grown increasingly intricate, eventually leading to the formation of organic coatings that surrounded the mineral particle. Over time, this coating could have pinched off, forming a primitive lipid membrane that encapsulated the entire metabolic system, creating a protocell, a precursor to the first true living cell. The iron-sulfur world presents a compelling vision of life arising not from a single molecule, but from a busy, energetic, and self-sustaining chemical economy anchored to a rock. So, if life's first spark was a chemical fire on a mineral surface, where did the very first organic ingredients for that fire come from? Could they have been delivered from a source even more primordial than the Earth itself? The leap from a chemical fire on a mineral surface to a living cell is immense, but what if that entire process was guided by an intelligence far beyond our own? This is the theory of directed panspermia, a concept that pushes the boundaries of science into the realm of cosmic purpose. It suggests that life on Earth did not arise by chance, but was deliberately seeded here by an advanced extraterrestrial civilization. The Nobel Prize-winning scientist Francis Crick, one of the co-discoverers of the structure of DNA, seriously entertained this idea. He and his colleague Leslie Orgel proposed that a distant civilization, perhaps facing its own extinction, could have loaded interstellar spacecraft with durable, freeze-dried microorganisms. These tiny ambassadors of biology would then be sent on a one-way voyage to promising young planets, effectively gardening the galaxy with life. Why would any civilization undertake such a monumental project? The motivations could be as varied as the stars themselves. Perhaps it was a pure act of altruism, a way to ensure that the flame of life would continue to burn somewhere in the cosmos even if their own world perished. It could have been a form of cosmic experimentation, a way to observe how life evolves under different planetary conditions. Or maybe it was simply the ultimate act of legacy, a way to leave an indelible mark on the universe. This theory carries staggering implications for our own story. If true, then every living thing on Earth, from the smallest bacterium to the largest whale, and indeed every human being, shares a heritage that is not just planetary but interstellar. Our entire evolutionary journey from that first cell to complex consciousness could have been part of a design set in motion billions of years ago. It blurs the line between science and science fiction, suggesting that our search for origins is not just a quest to understand chemistry, but a search for our cosmic parents. While critics point out that this idea simply moves the question of life's origin to another time and place, its power lies in the profound shift in perspective it offers. We are left to wonder if our planet was chosen, and if so, what our purpose here might be. If life was a deliberate gift from the stars, does that mean we are part of a grander cosmic community? From the fiery chemistry of mineral surfaces, a new kind of structure had to emerge. The lipid world hypothesis proposes that the true turning point was not a replicating molecule, but a simple protective bubble. Lipids are fatty molecules, the fundamental building blocks of all cell membranes. In the ancient world, these molecules could have formed naturally, perhaps near hydrothermal vents or even in shallow pools. Their most magical property is what happens when they are surrounded by water. Certain lipids are amphiphilic, meaning one end of the molecule is attracted to water while the other end repels it. To resolve this conflict, they spontaneously organize. They form a double-layered sheet with the water-loving ends facing outward and the water-fearing ends tucked safely inward. When disturbed, this sheet can curl in on itself, sealing off into a tiny, hollow sphere called a vesicle. This is not a complex biological process. It is simple chemistry and physics, as inevitable as oil forming droplets in water. These lipid vesicles became the very first frontiers, the first protected spaces. They created a fundamental division between an inside and an outside. Imagine a primordial vesicle forming in a rich chemical soup. It could accidentally trap within its watery interior a handful of amino acids, a short strand of RNA, or even a few charged mineral particles. Suddenly, those molecules are no longer drifting apart in a vast ocean. They are concentrated together in a microscopic laboratory, able to interact far more frequently and efficiently. But these bubbles were not just passive containers. They were dynamic and exhibited behaviors eerily reminiscent of life. As more lipid molecules in the surrounding solution attached themselves to the vesicle's surface, the membrane would grow. Eventually, the sheer physical forces would cause a large, unstable vesicle to pinch in the middle and divide into two smaller daughter vesicles. This is a primitive form of reproduction, a growth and division cycle driven entirely by chemistry. Some of the original encapsulated material would be shared between the two new bubbles, passing on a crude chemical inheritance. This provides a compelling pathway. A lipid vesicle that, by chance, enclosed a molecule capable of speeding up chemical reactions, or one that helped the membrane grow faster, would have an advantage. It would replicate more often, spreading its beneficial internal chemistry. This sets the stage for natural selection to begin acting at a pre-biological level. The lipid world suggests that containment came first. The establishment of a private, internal space was the essential innovation that allowed for the gradual refinement of the complex biochemistry happening inside. Before genetics could be perfected, it needed a home. The deep sea vents are not the only places where Earth's inner heat meets the surface. On the young volcanic land, another stage was set, one of boiling mud and steaming pools. This is the volcanic hot spring theory, a terrestrial alternative for life's cradle. Imagine a landscape of geysers and hot springs, much like Yellowstone National Park today, but on a planet still cooling from its violent birth. These pools are dynamic and unpredictable. Water, rich with dissolved minerals from the surrounding rock, constantly floods the porous ground, then is drawn back up by geothermal heat, only to be boiled and evaporated at the surface. This creates a relentless cycle of wetting and drying, a daily rhythm of concentration and renewal. A single drop of water in such a pool would experience a dramatic journey. It would be diluted one moment, then left to bake on hot rock as the water retreated, its dissolved organic compounds becoming intensely concentrated. In this thick, syrupy residue, molecules that would normally drift past each other in the open ocean are forced into close contact. This constant concentration is the key. It dramatically increases the odds that simple amino acids or nucleotides will bump into each other and link up, forming the long chains of proteins and RNA. The heat from the spring provides the energy to drive these reactions, while the mineral-rich surroundings, full of clays and metal oxides, act as catalysts to speed them along. Unlike the stable, high-pressure darkness of the deep sea vents, these terrestrial pools are a world of constant change, of intense light and dark, heat and coolness, flood and drought. This very turbulence could have been the catalyst for innovation, forcing early molecular systems to become robust and adaptable to survive. Could this relentless pulse of concentration and energy, this daily rehearsal of creation on land, have been the forge where the first truly resilient life forms were hammered into existence? If so, the journey from a steaming pool to a living cell required one final, crucial ingredient, a way to harness the most abundant energy source of all. The energy that fueled life's first spark may have come from a source far more ancient than the sun or the Earth's core. It might have been written into the very fabric of the cosmos at the moment of its birth. This theory connects our existence to the Big Bang itself through the cosmic microwave background. This is a faint, cold glow of radiation that fills every cubic inch of the universe, a silent echo of the primordial fireball. Today, it is incredibly weak, a relic cooled by 13.8 billion years of cosmic expansion. But in the distant past, this energy was far more intense. In the first few 100 million years after the Big Bang, the entire universe was bathed in a warm, uniform light. This was not a harsh, destructive radiation, but a gentle, all-pervasive warmth. The theory suggests this universal energy bath could have provided a subtle, consistent power source for the earliest chemical reactions. On any young, rocky planet with the right ingredients, this cosmic warmth could have gently encouraged molecules to link and interact, a soft hum of energy nudging chemistry toward complexity. The implications of this are staggering. It proposes that the specific conditions of the infant universe were not just a random setting, but a necessary cradle. The temperature, the density, the very quality of this background radiation might have been perfectly tuned to make the emergence of life not a fluke, but a cosmic inevitability. If this is true, then life is not an accident isolated to one lucky planet. It is a fundamental part of the universe's evolutionary story, a process that began when space-time itself was young. The same forces that sculpted galaxies and stars also quietly laid the groundwork for biology. This idea challenges our perspective on our place in the cosmos. Are we merely inhabitants of Earth, or are we a manifestation of the universe's inherent potential for life, a potential encoded into reality from its very first moments? If the universe itself set the stage, then what other fundamental forces could have played a role in writing life's first code? Deep beneath the ocean's surface, where hydrothermal vents meet the faint, filtering glow of sunlight, another powerful catalyst may have been at work. The zinc world hypothesis proposes that tiny crystals of zinc sulfide played a starring role in life's first energetic steps. These crystals are semiconductors, a property that allows them to absorb light energy and use it to power chemical reactions. In the shallow water vents of the early Earth, these glittering minerals would have formed a perfect stage. Bathed in the sun's ultraviolet light from above and bathed in a rich chemical broth from the vent below, they became nature's first solar panels. The process is both elegant and powerful. When a photon of ultraviolet light strikes a zinc sulfide crystal, it knocks an electron loose, creating a highly energetic, charged state. This activated surface becomes a reactive platform, hungry to balance its charge. It can then drive the reduction of carbon dioxide, pulling that carbon out of the air and using it to build the organic molecules essential for life, like formic acid or formaldehyde. Think of it as a primordial form of photosynthesis, but one that does not involve any living thing. It is pure geochemistry, a partnership between a mineral and sunlight, creating food from thin air. This theory beautifully bridges two worlds. It combines the surface catalysis of the iron-sulfur world with the power of photochemistry. The zinc sulfide crystals offer a structured, solid foundation for molecules to gather, just like other minerals, but they add a crucial ingredient, a direct and efficient way to tap into the vast energy of the sun. This solves a key problem faced by other vent theories, which rely solely on geothermal or chemical energy. Here, in these sunlit shallows, the building blocks of life could have been produced in abundance, powered by a constant, reliable source. The zinc world suggests that life did not have to choose between the deep, dark earth and the sunlit surface. It could have harnessed the best of both, using a mineral catalyst to convert cosmic light into chemical possibility, setting the stage for everything that followed. The sunlit shallows and volcanic pools were not the only potential cradles. Our planet held another, more potent energy source locked within its very rocks. Along the coastlines of the primordial world, the endless rhythm of the tides created a unique and powerful environment. Waves relentlessly pounded the volcanic rock, grinding it down into black sand beaches. This sand was not ordinary, it was rich with heavy minerals including uranium and thorium. These elements are radioactive, and as they slowly and predictably decay over billions of years, they release a steady stream of energy in the form of radiation. The action of the waves acted like a natural ore concentrator. Lighter grains of sand were washed back out to sea, while the denser, radioactive particles were left behind, accumulating in thick, concentrated layers along the shoreline. These beaches would have literally glowed with a faint, persistent energy, not from light but from atomic decay. This radiation is not merely a destructive force. In the right context, it can be a powerful driver of chemical change. The theory suggests that in the shallow, tidal pools that formed on these radioactive beaches, a remarkable alchemy could have taken place. The constant, localized energy from the decaying minerals would have bombarded the water and the simple organic molecules within it. This energy could have broken molecular bonds and forged new ones, driving the synthesis of more complex compounds. Imagine a tide pool that was not just warmed by the sun, but energized from within by the very sand beneath it. This environment provided a unique combination of factors. The tidal cycle ensured a regular mixing of new ingredients and a concentration of products as water evaporated. The radioactive sand provided a relentless, penetrating energy source that worked day and night, unaffected by weather or the darkness. And the porous, mineral-rich nature of the beach itself could have offered countless microscopic nooks and crannies, acting as protective reaction chambers where newly formed molecules could be sheltered and interact. This presents a starkly different vision of life's nursery, not a deep-sea chimney or a warm little pond, but a dynamic, energetic shoreline powered by the slow, silent fire of atoms. The first steps toward biology might have been taken on a beach that hummed with the latent power of the Earth's core, a power that would one day be harnessed by human hands. These radioactive beaches were not the only environments rich in carbon. Another theory suggests the very soot of the cosmos provided the scaffolding for life. This is the pH world hypothesis. Polycyclic aromatic hydrocarbons are not simple molecules. They are large, flat sheets of carbon atoms fused together in elegant hexagonal rings like microscopic chicken wire. You find them everywhere in the dark clouds of interstellar space, on asteroids and comets, and they would have been plentiful on the young Earth, raining down in a constant cosmic drizzle. Their stability is their greatest strength, allowing them to survive journeys through space and harsh planetary conditions. In the warm, shallow waters of the early planet, these pHs began to exhibit a fascinating behavior. Because their flat surfaces repel water while their edges are slightly attracted to it, they naturally stack on top of one another like a pile of microscopic plates. These stacks could then grow, forming sturdy, column-like structures. These were not random piles of molecules, they were the first potential architectural frameworks. Some scientists propose that these pH stacks could have acted as primitive membranes, creating compartments that separated an internal environment from the outside world, much like lipid vesicles. But there is an even more intriguing possibility. The specific pattern of atoms in different types of pHs could have acted as a crude code, a form of molecular information. Imagine information being stored not in a long chain like DNA, but in the unique stacking sequence of different pH molecules, one on top of the other. A stack with a certain sequence of pH types could carry a specific chemical message, a precursor to genetic data. This means the same universal soot could have provided both the physical structure for the first cells and a primitive system for information storage. The universe was not just delivering simple ingredients like amino acids, it was delivering sophisticated, multi-functional construction kits. The abundance of pHs across the galaxy suggests that this particular path from chemistry to biology might be a common one, a universal toolkit available on countless worlds. If stacks of cosmic soot were indeed life's first hard drives, how did that information ever learn to replicate itself and break free from its mineral confines? Every living cell, from the simplest bacterium to the neurons in your brain, runs on a remarkable kind of power. It is not fueled by fire or electricity in the way we commonly think, but by a subtle, invisible force, a difference in concentration across a barrier. This is the proton gradient, and it may be the most ancient form of energy on Earth. The chemiosmotic theory for the origin of life proposes that this fundamental process came first, long before genetics. The most likely place for this to happen was at those hydrothermal vents where the architecture of life itself was forged from rock and chemistry. The vents constantly release a fluid that is rich in hydrogen gas, which is a source of protons. This acidic, proton-rich fluid meets the cooler, more alkaline ocean water. Between them, the fragile mineral walls of the vent structures, often made of iron sulfide, act as a natural barrier. This setup creates a perfect battery, a persistent natural gradient where protons desperately want to flow from the acidic side to the alkaline side to balance the concentration. This flow is a form of potential energy, and it is immense. The theory suggests that the first biological systems were not molecules that copied themselves, but simple, bubble-like structures that learned to harness this proton power. Imagine a primitive vesicle, a lipid membrane, forming right within the porous mineral wall of a vent. It would find itself straddling this energy-rich gradient. If this vesicle happened to contain a simple molecular machine, perhaps a protein that formed a channel, it could allow protons to flow through it in a controlled way. This controlled flow of protons could then be used to drive other crucial chemical reactions inside the vesicle, like stringing together amino acids or building nucleotides. It would be like a tiny water wheel using the flow of a river to turn a millstone. The energy was not invented by life, it was discovered. Life simply found a way to plug into a planetary power source that was already running. This idea turns our understanding of early life on its head. Instead of a complex genetic code emerging to manage a cell's functions, the first function was energy capture. Genetics came later as a way to record and refine the designs of the most successful energy harvesting systems. The very process that powers your cells today might be a billion-year-old relic of life's first and most important discovery, the art of tapping into the Earth's own energetic heartbeat. But this ancient energy harnessed by the first protocells required a set of instructions to become sustainable. Another theory presents a radical and controversial architect for that code, one we usually associate with disease. The viral origins theory suggests that viruses, or something very much like them, were not latecomers to the world of life, but its very pioneers. We typically think of viruses as simple parasites, biological hijackers that can only replicate by invading a living cell. This theory turns that view completely on its head, proposing that the first self-replicating entities were nothing more than naked strands of RNA, adrift in the primordial soup. These molecules were the ultimate minimalists, possessing just one crucial talent, the ability to make copies of themselves. In the beginning, they were likely solitary and selfish, acting as molecular parasites. An RNA strand would use the chemical resources around it, the free-floating nucleotides, to build a duplicate. This was not life as we define it, but a persistent autocatalytic chemistry. The true innovation came when these replicators began to interact. Some strands might have developed the ability to produce simple proteins that offered a benefit, perhaps by protecting the RNA from breaking down or by helping it replicate faster. If one of these more advanced strands found itself enclosed within a lipid vesicle, a remarkable partnership could have begun. The vesicle offered shelter, concentrating the replicator and its resources, while the replicator's activities might have helped stabilize or even grow the vesicle. This was not a peaceful symbiosis, but a primitive form of warfare and cooperation. Different RNA replicators would have competed for resources and for space inside protective bubbles. The most successful ones would be those that could best manipulate their environment, effectively turning their vesicle into a host. This constant struggle between replicator and container, between parasite and its protective shell, could have been the driving force that led to increasing complexity. The pressure to survive would have selected for replicators that could build better membranes, manage energy, and eventually create the sophisticated machinery of the first true cells. In this light, every living cell on Earth could be the descendant of a truce struck between a selfish replicator and a protective bubble, a peace treaty that ended a molecular war and began the story of biology. The viruses we fight today might be the distant feral relatives of our own ancestral code, a perpetual reminder of life's contentious and parasitic beginnings. The endless molecular warfare of the primordial soup was not the only path to complexity. Far from the warmth of any star, in the vast, dark clouds that drift between the stars, another kind of chemistry was unfolding in the cold. This is the cosmic ice theory, which suggests that the deep freeze of interstellar space was a surprisingly productive workshop for life's ingredients. Within these colossal nebulae, temperatures hover just a few degrees above absolute zero. Tiny dust grains, mostly silicates and carbon, are suspended in this void, and they become coated in a thick mantle of frozen ices, water, carbon monoxide, ammonia, and methane. To us, this sounds like a sterile environment, a place where all chemical activity grinds to a halt. But these dark clouds are constantly bathed in cosmic radiation, high-energy particles streaming from distant supernova and other cosmic events. This radiation is the unexpected catalyst. When a cosmic ray slams into one of these icy dust grains, it shatters the frozen molecules, creating a soup of highly reactive fragments or radicals. Trapped together in the solid ice matrix, these fragments have nowhere to go. As the ice slowly warms from the energy of the impact or from a nearby stellar flare, these radicals can move just enough to find each other and link up, forming entirely new, more complex molecules. In laboratory experiments that simulate these conditions, scientists have watched in awe as simple ices are bombarded with radiation and transform into a rich organic tar, containing amino acids, the components of lipids, and even the nucleobases that form RNA and DNA. The cold, far from being a barrier, acts as a protective trap, holding the reactive pieces in place long enough for them to assemble. These icy grains, now laden with complex organics, become the seeds of future worlds. They are the raw material from which comets and asteroids coalesce. When one of these icy bodies later smashes into a young planet like Earth, it does not deliver just simple chemicals. It delivers a pre-made toolkit, a concentrated payload of sophisticated organic compounds that were forged in the chill of deep space. The water that fills our oceans and the very letters of our genetic code might have been printed in the frozen darkness long before our sun even began to shine. That very struggle between replicators hints at a deeper principle, a chemical logic that could build life from the bottom up. Autocatalytic sets offer a vision of life not as a single replicator, but as a self-sustaining chemical network, a web of mutual creation. Imagine a small pool of different molecules, each one relatively simple. On its own, each molecule might form slowly or not at all. But if one molecule, by chance, can speed up the chemical reaction that creates a second molecule, and that second molecule can, in turn, catalyze the formation of a third, a powerful dynamic can emerge. If this chain of catalysis eventually forms a closed loop where the last molecule helps create the first one again, the entire system becomes self-feeding. This is an autocatalytic set, a community of molecules where every member is both a product and a catalyst, each helping to make another. Once such a network is established, it is incredibly robust. It does not need an instruction manual to persist. It simply maintains itself through the constant, interdependent production of its own components. If one molecule is removed, the others in the loop can work to replenish it. This is a metabolism-first model in its purest form. Long before any molecule learned to copy itself with perfect fidelity, these swirling, interactive networks could have grown in complexity. A simple set might incorporate new molecules from its environment, expanding its web of reactions. Some sets would be more stable or efficient than others, persisting longer and dominating the local chemistry. This is evolution in its most fundamental chemical sense, a competition between different, self-sustaining reaction networks. The brilliance of this idea is that it sidesteps the chicken and egg problem of genetics and metabolism. Which came first, the molecule that copies information or the system that harnesses energy? In the autocatalytic world, they are one and the same. The information is stored in the very structure of the network itself, in the specific pathways of reactions that sustain it. This swirling chemical society could have been the foundation upon which everything else was built. Eventually, these networks might have become enclosed within lipid membranes, creating the first true protocells. The most successful sets would be those that could not only sustain themselves but also grow and divide, taking their entire, intricate economy with them. So we are left to wonder if our own cellular metabolism, with its dizzying cycles like the Krebs cycle, is a modern, highly refined echo of one of these primordial, self-inventing chemical webs. Was life's first spark not a single molecule, but an entire, self-perpetuating conversation between many? That universal energy currency app powers every thought and motion in your body right now. The thermosynthesis theory proposes a beautifully simple origin for this entire system, rooted not in complex chemistry, but in the most basic rhythm of the early Earth, the daily pulse of heat and cold. Before the sophisticated machinery of photosynthesis or respiration existed, the first life forms might have run on a kind of natural temperature engine. Picture a shallow tidal pool on a primordial coastline. As the sun rose each day, the water would grow warm, causing the molecules within it to vibrate with increasing energy. Then, as night fell, the pool would cool down significantly. This constant, predictable cycling between hot and cold could have been the driving force for life's first metabolic reactions. The theory suggests that early, floppy proteins could have acted like tiny, molecular springs. In the heat of the day, these protein springs would stretch open, creating a strained, high-energy configuration that allowed them to capture a raw chemical group called a phosphate. Then, when the cool of night arrived, the protein would snap shut, using that mechanical force to forge a powerful, high-energy bond, attaching the phosphate to a molecule called ADP, thereby creating ATP. This process would be a primitive form of thermosynthesis, a direct conversion of environmental heat cycling into stored chemical energy. It is an incredibly elegant mechanism because it requires no complex light harvesting systems or intricate electron transport chains. It relies only on a simple protein and a reliable environmental cycle that was available almost everywhere on the planet. The first organisms would not have needed to seek out energy. They simply had to exist within the natural ebb and flow of temperature, harnessing that universal rhythm to power their internal chemistry. This idea transforms our view of early life from an active hunter of energy to a passive harvester of a planetary cycle. The daily rising and setting of the sun did not just provide light, it may have wound the very springs of life, charging the first biological batteries with a gentle planetary breath. If life learned to power itself by the simple turning of the world, what other fundamental rhythms could have shaped its next great evolutionary leap? The very ground beneath our feet might have been the first scribe of life's instructions. Another theory proposes that silicate minerals, the most common compounds in the Earth's crust, did more than just concentrate molecules. They could have acted as the original templates for our genetic code. This silicate world hypothesis takes the clay catalyst idea a step further, suggesting that the intricate, repeating patterns etched into the surfaces of certain crystals directly guided the formation of the first nucleic acids. Imagine a silicate crystal as a sheet of paper with a pre-printed geometric grid. The specific arrangement of atoms on its surface, with its regular pattern of positive and negative charges, would have been a perfect attractor for the building blocks of RNA. These nucleotide molecules drifting in the primordial waters would have stuck to the crystal, slotting into place according to the mineral's own atomic layout. The silicate surface would not just be holding them still, it would be actively organizing them, forcing them into a specific sequence that mirrored the crystal's own structure. This process would be like a molecular printing press, using the unchanging pattern of the rock to stamp out identical strands of a primitive genetic polymer. Over time, as these mineral-bound chains grew longer, they might have reached a point of complexity where they could peel away from their rocky template, now carrying a sequence of information that was originally dictated by the geology of the planet itself. This is a profound bridge between worlds. It suggests that the transition from a non-living, rocky Earth to a living, biological one was not a sudden leap but a gradual handoff. The first genes may not have been born from random chemistry alone, but were literally printed onto molecules by the inorganic crystals that dominated the early landscape. Our most fundamental biological information, the very blueprint for life, could have a direct lineage stretching back to the crystalline order of common rocks. If our genetic heritage is written in stone, what other planetary forces might have contributed their own verses to the code of life? Those silent, frozen architects from the depths of space may have delivered more than just the letters of our genetic code. Comets are the great ice vaults of the solar system, and their role in our origin story could have been both constructive and spectacularly violent. While Panspermia suggests life itself made the journey, this theory proposes a more foundational delivery, the essential ingredients and the energy to cook them. A comet is far more than a simple ball of ice. It is a dusty snowball, a frozen repository containing vast amounts of water ice, but also a stunning array of complex organic molecules. We have learned from missions like Rosetta that comets carry amino acids, the building blocks of proteins, and even alcohol and sugar molecules. They are, in essence, pre-packaged kits of life's essential chemistry, forged in the cold of the protoplanetary disk and preserved in a deep freeze for billions of years. Now picture the early Earth, a hot, rocky world still cooling from its formation. Its surface was likely largely dry, with any original water vapor locked in the atmosphere or lost to space. Then came the late heavy bombardment, a period of intense cosmic artillery when countless comets and asteroids rained down upon the young planets. Each comet impact was a cataclysm, but also a delivery of unimaginable value. A single, large comet could have delivered a significant fraction of the water that now fills our oceans, but it brought something even more precious, a concentrated payload of those complex organic molecules scattered across the planet's surface. The impact itself provided the final, crucial ingredient, energy. The tremendous heat and pressure of a comet striking the Earth would have been like thrusting a frozen meal into a blast furnace. This was not mere destruction, it was a form of cosmic chemistry. The instantaneous, intense energy could have shattered the comet's complex molecules, breaking them down into highly reactive fragments. Then, in the cooling aftermath, within the warm, mineral-rich impact craters and the newly delivered water, those reactive pieces would have reassembled into an even richer and more diverse soup of organic compounds. The impact site became a pressure cooker, a natural laboratory where the ingredients were delivered, mixed, and energized all at once. This theory elegantly solves multiple problems at once. It explains the source of Earth's vast oceans. It accounts for the abundance of prebiotic molecules on the early planet, and it provides a powerful, localized energy source to drive the chemistry forward, starting the process toward life in specific, fertile locations. The comets did not just bring the flour and sugar for the primordial cake, they also lit the oven, creating the perfect conditions for the first, tentative steps from chemistry toward biology. If our oceans and our organic heritage were gifts from the icy depths of the solar system, does that make every living thing on Earth, in a very real sense, a citizen of the cosmos? That delicate balance of our planet points to a far greater cosmic architecture. The Goldilocks zone theory expands our view from the chemistry of a single world to the grand dynamics of an entire solar system. This is the concept of the habitable zone, the narrow orbital band around a star where conditions are just right, not too hot and not too cold for liquid water to exist stably on a planet's surface. Water is the universal solvent, the essential medium in which the molecules of life can dissolve, mix, and react, but liquid water alone is not enough. A true cradle for life requires a symphony of stable conditions. The planet needs a sufficient mass to hold onto a protective atmosphere, one that can shield the surface from lethal ultraviolet radiation and sterilizing cosmic rays. It likely requires a molten iron core spinning to generate a global magnetic field, a force field that deflects the solar wind and prevents that precious atmosphere from being stripped away into space. Our Earth was the ultimate Goldilocks planet, blessed with all these attributes in perfect harmony. Its orbit was stable, its climate was tempered, and its geology was active, recycling chemicals and regulating temperatures over billions of years. This theory suggests that while the organic ingredients for life may be universal, scattered on comets and asteroids, the planetary conditions needed to nurture those ingredients into biology are exceptionally rare. A world too close to its star becomes a scorching Venus, its oceans boiled away under a thick, suffocating blanket of greenhouse gases. A world too far becomes a frozen Mars, its water locked in ice and its atmosphere thin and barren. The window for life is incredibly narrow. This perspective makes life seem both special and statistically improbable, a precious flame flickering in the vast cosmic dark. Yet, given the sheer number of stars in our galaxy alone, numbering in the hundreds of billions, the law of averages suggests that other Goldilocks worlds must exist. Life may not be a miracle, but a natural outcome on those rare, perfect worlds that possess the patience and stability to allow chemistry to blossom into biology. We are likely not alone, but we may be separated by immense stretches of space and time, isolated oases of life in a galaxy where habitable real estate is the most valuable commodity of all. The solid ground of chemistry and energy suddenly dissolves into a realm of pure probability. At the most fundamental level of reality, the rules are not the ones we know. In the quantum world, particles can be in two places at once. They can tunnel through seemingly impenetrable barriers, and they can become spookily connected across distances. The quantum biology origins theory asks a breathtaking question. What if life did not just emerge from chemistry, but from these very quantum effects? This is not about the chemistry of molecules, but about the behavior of the subatomic particles within them. Consider the very first energy transfer, a process vital for any living system. In our classical world, an electron must have enough energy to jump from one molecule to another. But in the quantum world, that electron does not have to go over the barrier. It can simply appear on the other side, a trick known as quantum tunneling. This is not magic, it is a proven physical phenomenon. If this effect was at play in the dense molecular chaos of the early Earth, it could have dramatically accelerated the most crucial reactions. The transfer of energy, or even of a single proton, could happen with an efficiency that classical physics cannot explain. This quantum boost might have been the difference between a reaction that was impossibly slow and one that was fast enough to sustain a primitive metabolism. The implications grow even stranger with the concept of quantum coherence. This is the idea that a quantum system can exist in a superposition of multiple states at the same time, effectively exploring many possibilities simultaneously. Imagine a primitive molecule on the cusp of self-replication. In a coherent state, it would not be limited to testing one chemical pathway at a time. It could, in a sense, test multiple ways to copy itself all at once, instantly finding the most efficient route. This quantum search engine could have guided random chemistry toward biological function with a speed and precision that seems almost directed. The most radical suggestion is that these quantum processes were not just passive effects, but active participants in selecting the very pathways that led to life. The bizarre, counterintuitive laws that govern the tiny building blocks of reality may have provided the invisible scaffolding that allowed biology to assemble itself. If true, then the spark of life is not just a chemical event, but a quantum phenomenon woven into the fabric of the universe itself. Deep in the planet's crust, another kind of engine was quietly humming. The methanogen first hypothesis proposes that the very first life forms were not generalists, but specialists already perfectly adapted to their world. These pioneers were likely similar to modern archaea, a whole domain of life distinct from bacteria and eukaryotes, and they had a unique metabolism. They were methanogens, microscopic beings that consumed simple, abundant gases like hydrogen and carbon dioxide, and as their waste product they released methane. On the early Earth, this was a perfect survival strategy. The atmosphere was thick with hydrogen, a potent energy source, and completely devoid of the corrosive oxygen that would come much later. For these organisms, the entire planet was a buffet. They did not need sunlight, nor did they rely on complex organic molecules drifting in the ocean. Their food was the planet itself, bubbling up from volcanic vents or seeping from the rocks. They harnessed the energy from the simple chemical reaction between hydrogen and carbon dioxide, a process called methanogenesis. This is one of the most ancient and simplest biological pathways we know. The genetic evidence for this is compelling. When scientists construct the tree of life, tracing back genetic lineages to find our last universal common ancestor, the branches that lead to modern methanogens are among the deepest and most ancient. This suggests that the earliest successful life forms, the progenitors of everything that followed, might have been these methane-producing microbes. Their existence would have fundamentally transformed the planet. As they multiplied, they began to change the very composition of the atmosphere, pumping out methane, a powerful greenhouse gas. This methane blanket could have played a crucial role in warming the young Earth, which was still cooling and might have otherwise been a frozen world. Their waste product, in effect, helped to create a stable, warm climate, a comfortable cradle for the next, more complex stages of life to emerge. So the first inhabitants of our world may not have been struggling in a soup, but were already masters of their environment, tiny chemical engineers whose life's work was to reshape the planet itself, setting the stage for all of us. But that intricate dance of energy and information requires a crucial element, a kind of molecular glue that holds the entire system together. This is the phosphate world theory, which argues that the emergence of life faced a severe and unexpected bottleneck, a shortage of available phosphorus. Today, phosphate is a fundamental pillar of biology. It forms the energetic currency of ATP, the backbone of the DNA double helix, and the structure of RNA. Without it, life as we know it simply could not function. Yet on the early Earth, soluble phosphate was incredibly scarce. The problem was chemistry. Most of the planet's phosphorus was locked away in insoluble minerals like apatite, a tough, rocky vault that primitive chemistry could not easily crack. For life to begin, it needed a key to open that vault. One potential key came from the sky. Meteorites, particularly a class known as Schreibersite-rich iron meteorites, delivered phosphorus in a far more reactive and soluble form. When these meteorites landed in water, the mineral Schreibersite would have corroded rapidly, releasing its phosphorus into the environment in a state that was immediately usable for forming the first nucleotides and energy-carrying molecules. Another solution may have emerged from the Earth itself. Certain environments, like acidic volcanic pools or regions with high concentrations of specific organic acids, could have slowly dissolved the apatite minerals, trickling precious phosphate into the primordial soup. The moment this bottleneck was overcome was a pivotal turning point in planetary history. With a newfound, reliable supply of phosphate, the building blocks of genetics and energy metabolism could finally be assembled in earnest. It was as if the universe had been waiting for this one ingredient to complete the recipe. The sudden availability of this molecular glue could have triggered an explosion of biochemical complexity, allowing for the stable formation of long RNA chains and the efficient storage of chemical energy. The leap from simple organic molecules to a self-sustaining, replicating system may have hinged on this single element's liberation from its rocky prison. The identity of our very first ancestor is one of biology's greatest mysteries. We call it LUCA, the last universal common ancestor, the single cell from which every living thing on Earth supposedly descended. But what if that picture is wrong? What if LUCA was not a single organism at all, but a thriving, chaotic community? This is the community LUCA theory, and it reimagines the dawn of life. Instead of a lone pioneer, picture a vast, interconnected population of primitive cells, all swimming in the same primordial pond. These early entities, often called progenotes, were not the sophisticated cells of today. They were messy and rudimentary, with sloppy genetic replication and porous membranes. Their greatest strength was their openness. They freely swapped genes with one another, trading bits of genetic code like a bustling molecular marketplace. A cell that developed a better way to harvest energy could share that innovation with its neighbors. Another that found a way to repair its membrane could pass the instructions along. In this world, individuality was a fluid concept. The entire community acted as a single, distributed network of genetic and metabolic capabilities. The gene for a useful protein was not the private property of one cell line, but a communal tool available to all. This constant, rampant sharing of genetic material solves a major puzzle in evolution. The fossil record shows an incredible diversity of life appearing in a surprisingly short window of time. If life had to evolve from a single, isolated cell through slow, linear descent, this explosive diversification seems almost impossible. But if the earliest life was a communal enterprise where innovations could spread horizontally across the entire population almost instantly, then rapid diversification makes perfect sense. A breakthrough in one corner of the community could become common knowledge everywhere within a short period. Cellular individuality, the idea of a discrete organism with its own private genome, would have emerged later. It was a trade-off. As cells became more complex and specialized, they likely built more stable membranes and more accurate replication machinery. This increased their private efficiency but gradually closed the doors to the free-for-all genetic exchange of their ancestors. The boundaries between them hardened, and distinct lineages finally crystallized out of the communal soup. So you are not descended from a single winner in the primordial lottery. Your heritage traces back to an entire collaborative society, a collective that learned to survive by sharing its most precious resource, information. What if this communal nature was a necessary phase, a required step to achieve the complexity that followed? Even as comets delivered the ingredients for life, their impacts also brought global destruction. The early Earth was a shooting gallery bombarded by asteroids and comets in a period known as the Late Heavy Bombardment. These collisions released energies that would have vaporized oceans and sterilized the planet's surface, boiling away any delicate chemical progress toward life. For life to begin, it needed a sanctuary, a place to hide. The impact-shielded refugia theory suggests that life did not emerge in the open, but in deeply protected niches, safe from the celestial chaos above. The most likely sanctuaries were far underground, within the fractured bedrock of the planet itself. Miles below the surface, in networks of tiny pores and cracks filled with water, the first biochemical systems could have developed in perfect peace. Here, the temperature was stable, and the rock overhead acted as a colossal shield. absorbing the immense shock waves and radiation from even the largest impacts. The surface might have been turned into a molten hellscape, but deep in these subterranean aquifers, the water would have remained liquid and the chemistry undisturbed. Another perfect refuge existed at the bottom of the ocean within the labyrinthine structures of hydrothermal vents. While a direct impact would devastate the area, the vast volume of the ocean acted as a buffer, absorbing and dissipating the energy. More importantly, the vent systems themselves are extensive networks with countless smaller chimneys and porous rock formations. A community of primitive metabolic systems or protocells established in the deep, shielded recesses of such a network could have survived a nearby strike. The devastation on the surface would have passed them by as a distant rumble. This idea transforms our search for life's cradle. It was not necessarily the most chemically rich environment, that one, but the safest one. The first living things were not hardy pioneers braving a violent world, but fragile fugitives, their existence dependent on finding a haven where they could experiment in peace for millions of years. This need for sanctuary might be a universal rule. If we hope to find life on other worlds, like Mars or the icy moons of the outer solar system, we should not look to their surfaces, but deep beneath them, in the eternal, protected dark where life first learned to wait out the storm. That simple chemical factory running on planetary gases might have been powered by one of life's most ancient and fundamental circuits. The acetyl-CoA pathway is a direct and elegant form of metabolism, a biological engine that some scientists believe was the very first to turn over. It is a form of autotrophy, the incredible ability to build the complex molecules of life from simple, inorganic ingredients. Forget needing a pre-made soup of organic compounds. This pathway takes carbon dioxide straight from the air and hydrogen gas from volcanic vents and forges them into acetyl-CoA, a central molecular hub from which all the essential building blocks of a cell can be constructed. Think of it as the ultimate one-stop shop. From this single product, an organism can manufacture its sugars, its fats, and the very amino acids that form its proteins. The sheer efficiency and simplicity of this process are what mark it as primordial. This pathway is not found in the more complex plants and animals. It is the signature metabolism of some of the most ancient lineages of archaea and bacteria, organisms that thrive in environments that mirror the early Earth. The machinery that runs this pathway is built around metals, specifically nickel and iron. These metals act as the core catalysts, the molecular wrenches and gears that make the critical chemical reactions possible. On the young planet, these metals would have been plentiful, leaching from rocks into the acidic, hot waters of hydrothermal systems. The raw fuel was equally abundant. The early atmosphere was rich in carbon dioxide, and hydrogen gas billowed from countless volcanic fissures on the seafloor. All the necessary parts were simply lying around, waiting to be assembled. The first life forms, then, may not have been consumers of complex organics, but sophisticated chemical artisans. They were masters of geochemistry, tiny refineries that learned to harness the planet's own exhaust to build themselves from scratch. They took the breath of the world and the fire of the earth and transmuted them into biology. This vision completes a profound cycle, suggesting that life did not just emerge in a receptive environment, but actively forged itself from the very minerals and gases that define the planet. These first membranes did not need to be sophisticated fortresses. The semi-permeable ester world theory proposes that the original cellular barriers were not made of the complex phospholipids we see today, but from far simpler molecules called esters. Picture the earliest protocells not as sealed vaults, but as loosely woven baskets. Esters are organic compounds that can form spontaneously from simple alcohols and acids, chemicals that would have been abundant in the primordial soup. Their molecular structure creates a membrane, but one that is naturally more leaky and flexible than a modern phospholipid bilayer. This permeability was not a design flaw, it was the key to survival. Before the evolution of intricate pumps and channels to shuttle nutrients and waste across a cell membrane, how would a primitive protocell eat or breathe? It relied on passive diffusion, the simple movement of molecules from an area of high concentration to low concentration. A highly impermeable phospholipid membrane would have been a death sentence, trapping the cell's contents and starving it of new building blocks. An ester membrane, however, was the perfect solution. It was selective enough to maintain a distinct internal environment, concentrating the precious molecules of a primitive metabolism or replication system. Yet it was porous enough to allow small, essential molecules like amino acids, nucleotides, and ions to drift in and out freely. The cell did not need to work for its food, the food simply came to it. This created a dynamic and open system where the protocell could continuously sample the chemical richness of its surroundings, incorporating new molecules as its internal chemistry churned away. The membrane was a gentle filter, not a solid wall. This theory elegantly solves a major puzzle in the origin of life. How could the first cells manage the flow of materials without any of the complex machinery that even the simplest modern bacteria possess? The answer is that they did not need to manage it at all. They outsourced the problem to physics using a simple, self-assembling membrane that was inherently fit for purpose. The transition to more stable, less permeable phospholipid membranes likely occurred later, as natural selection favored cells that could better control their internal conditions, especially as the external environment became more competitive or variable. The first living cell may have been less a defined entity and more a persistent, swirling chemical reaction, contained by nothing more than a delicate gossamer film that let the world flow through it. Our search for life's origins forces us to look beyond our own world to a place where the chemistry is utterly alien. Saturn's moon Titan offers a frozen glimpse into a potential alternative genesis. This theory suggests that the complex organic reactions occurring in Titan's thick, orange haze could represent a completely different pathway for the emergence of life. Titan's atmosphere is a vast, ongoing photochemical experiment. The sun's ultraviolet radiation constantly bombards a soupy mix of nitrogen and methane, breaking these simple molecules apart. The resulting fragments are highly reactive radicals which then link together in the cold, upper air, forming increasingly complex organic compounds. These molecules, including benzene and hydrogen cyanide, eventually clump together into larger particles and drift down to the surface like a slow cosmic snow. This photochemical process is a non-biological engine for manufacturing the very sorts of complex organics that, on Earth, became the building blocks of biology. But on Titan, the entire system runs on a different solvent. Instead of water, Titan has lakes and rivers of liquid methane and ethane, flowing across a landscape of water ice as hard as rock. This raises a profound question. Could a form of life fundamentally different from our own arise in those frigid methane seas? The possibility of methane-based life forces us to reconsider the universal principles of abiogenesis. Life on Earth is built on carbon chemistry in a water medium, but the core requirements might be more abstract: a need for a solvent that can dissolve and transport molecules, a source of energy to drive reactions, and a molecular system capable of complexity and information storage. Titan possesses all these, just with a different set of ingredients. It has the liquid methane solvent, energy from solar radiation, and perhaps even from internal processes, and a chemistry demonstrably capable of creating vast libraries of complex carbon-based molecules. The photochemical origin theory on Titan teaches us that the journey from chemistry to biology might not be a single, narrow road that only Earth discovered. It could be a sprawling network of potential highways, each with its own unique rules and conditions. If life can start in the warm, sunlit ponds of Earth and also in the frozen, methane-darkened rivers of Titan, then the universe may be teeming with possibilities we are only beginning to conceive. Our journey through these theories of life's origin reveals a common thread, a shift from seeing life as a mere passenger on a planet to an active participant in its own creation. The Gaia hypothesis offers a profound culmination of this idea, proposing that life and its planetary environment are not separate entities, but a single, intertwined, self-regulating system. It suggests that from the very beginning, the first organisms did not simply adapt to a pre-existing world. They began to actively engineer it. Consider those ancient methanogens consuming hydrogen and exhaling methane. Their collective waste product, a powerful greenhouse gas, wrapped the young Earth in a protective blanket, preventing it from becoming a frozen wasteland and stabilizing the climate for more life to flourish. This is a perfect example of a feedback loop where life's activity alters the environment in a way that, in turn, supports more life. The Great Oxidation Event is another monumental example. When the first cyanobacteria evolved photosynthesis, they began releasing a toxic waste gas, oxygen, into the atmosphere. This was a planetary catastrophe for the anaerobic life that dominated the world, causing a mass extinction. Yet, this same crisis eventually led to the formation of the ozone layer, which shielded the planet from harmful ultraviolet radiation and allowed life to colonize the land. The very air we breathe is a testament to life's power to transform its own home. This perspective transforms our understanding of life's emergence. It was not a passive chemical accident that occurred in an isolated pond or vent. It was the ignition of a dynamic planetary scale process. The first living things were not just inhabitants of Earth, they were partners in its ongoing creation, engaging in a constant dialogue with the air, the water, and the rocks. Life did not just find a niche on this planet, it helped build that niche layer by layer over billions of years. This final theory leaves us with a humbling and powerful thought. We are not just living on the Earth, we are part of a living Earth, a continuous expression of a process that began when the first metabolic fire was lit, an unbroken chain of co-evolution that connects us directly to the very first organisms that dared to change their world. We have traveled from the deep sea vents to the interstellar clouds, from the first metabolic sparks on iron sulfide to the quantum possibilities that may have guided the way. 30 distinct visions, each a brilliant attempt to solve the oldest mystery. The fact that we can even ask these questions, that we can run these experiments and peer back through billions of years, is a testament to human curiosity itself. We may not have a single, definitive answer, and perhaps we never will. The true story of life's beginning might be a tapestry woven from many of these threads, a little bit of chemistry from a comet, a metabolic cycle from a vent, and a genetic code printed on clay. The journey of discovery is as profound as the destination, so we leave you with this final question, one that now belongs to you. After this journey through the cosmos and back in time, which of these paths feels most true to you? Which theory resonates as the most plausible starting point for everything we are? Share your thoughts in the comments. We are genuinely curious to hear your perspective. And if you want to continue exploring the universe's greatest mysteries with us, please like this video, subscribe to the channel, and tap the bell so you never miss our next adventure into the